Yeah, hi. Oh, now it goes full screen. I'm going to talk about our project that's about AI that satisfies without overdoing it, which is a euphemism for without killing all of us. We had quite a few team members listed here are just the ones that are part of AI Safety Camp. We also have a few people from SPAR and some interns of Jobst that were working with us. Okay, the one sentence summary of our project, quite a long sentence, but the working hypothesis is that if you maximize something that's not specified correctly, the wrong objective, something will go very wrong. And it's not clear what the right objective is, if it exists, and how we might write it down or learn it. Therefore, we want to think about what kind of algorithms can we use that do not maximize anything. And therefore, we do not talk about reward anymore. But instead talk about something called aspirations, which are basically just constraints on the state of the world. So we want to make the world be in this kind of aspirate for state. And we might also add some safety criteria to this algorithm. Like if we already know how to satisfy our aspirations, maybe we can do it in a way that's, for example, not especially impactful. The high-level framework is, okay, we have an agent and we have an environment. The agent might consist of a world model and an actor and some methods to perceive the world. And in a lot more detail, hopefully many of you are familiar with like Markov decision processes that are used in reinforcement learning. So here we have like a model state, and we have a decision algorithm that chooses an action, and then the model, like then the world gets affected and the model transitions to a new state. We are assuming that our world model is adequate for our purposes. So for now, we are not focused on learning the world model. And instead of talking about reward, we will just talk more generally about deltas. So we receive some changes in the evaluation metric when the state transitions. And the evaluation metric, like it measures something that we care about, but not something that we want to maximize. So it might be something trivial like amount of apples in my house or something like this that I might care about. In the future, it could be something more complex, for example, something multidimensional. And like last terminology, we talk about total just as the sum of deltas over all the steps of the episodes.
The evaluation metric could also be global mean temperature, to give another example.
Okay. So the basic algorithm has the shape that what we want from it is that on expectation, the total should equal a fixed aspiration value that we give it. And there might, again, be more complicated version with multidimensional versions or aspiration intervals, stuff like this. But for now, we talk about just setting an expectation value. And as a preparation, the algorithm will compute so-called feasibility sets, which are just the set of possible values of totals in states or for states if we take certain actions. And then the algorithm will work like this. It iterates over states and it chooses actions for each state, obviously, and it propagates also aspiration values. So each state has a state aspiration, and that's basically the achievement that we want to reach on average if we are in this state. And then for each possible action, we choose a feasible action aspiration. And then we pick two actions and randomize between them in such a way that the aspiration will be fulfilled on average. So the average of the state aspiration, of the action state aspiration should be the state action aspiration. And then, okay, we choose the action and the world transitions into a new state. And then we have to compute a new aspiration for this new state. And we have to do this in a way that the aspiration of this new state is on expectation equal to the state action aspiration for the action that we have chosen. And to illustrate this in a bit more detail, on the next slide, we have an example where for simplicity, we have just chosen a single action. So on top, you see, okay, we start in state ST, then we choose an action AT prime, and then the environment will stochastically go into one of these three states on the right. And on the bottom, you can see the feasibility sets, which are just the intervals that you see there. And you can see the aspiration as a dot. So we start out in state ST, And have this aspiration there, that's the dot in the middle. And then because we choose just one action, we have to propagate this aspiration to this action as well. And now when we look at the intervals of the states that might happen, we see that there's maybe a slight problem because these intervals don't really contain our aspired for value. But we only need to achieve it on average. So what we do is we look at the percentage position of the aspiration in the interval. And let's say it's around 10%. And then, okay, we say the aspirations for the other states should be also the 10% value in the interval. And then if you take the average over this just by linearity, you'll see that the expectation will be the one that we wanted for this state action combination. And that's how the algorithm works, basically. And now Martin will tell you a bit about safety criteria.
Thanks. The agent, as specified by this algorithm, still has some remaining degrees of freedom, which means that there are many policies that we can use to satisfy the aspirations. And we don't know whether all of these policies are safe. Some of them are probably unsafe. And we can actually do better than selecting some policy at random. And we can still satisfy the aspiration. And this is where the safety criteria come into play. This could probably be an entire project on its own, but we have discussed various safety criteria. And I would like to talk in particular about the change, which is, there are several ways to formulate it. One is we can compare the initial state with the terminal state and measure how different they are. Or alternatively, we can try to compare the final state with what the final state would have been if the agent didn't act. And we're going to show you some videos demonstrating how these criteria work in practice. On the right, you can see this is an example of a grid world. If you're familiar with, there was a paper, AI safety grid worlds, and we're the blue dot. The agent is the blue dot. The green square is our goal. And we would like to reach there. And there are some safety criteria which we can parameterize. On the left, we can set values for different safety criteria. So this one, here you see a loss coefficient for state. This specifies how much we want to disincentivize changing the state of the environment. And you can see that the agent moves this gray block and then moves it back so that the environment in the end is as similar as it was in the beginning as possible. And if we change this criteria to the other extreme, I think the video restarted from the beginning. If we change this criteria to the other extreme, then we incentivize the agent to do as much change to the environment as possible. And you can see that now the gray block goes to a different position. So we can control the behavior of the agent by these safety criteria. And there is one more example. So here we have this gray vertical pane, which you can think of it as maybe a window, something that can break if you push it from the side. But if you push it from the bottom, then it just moves and it's not broken. And we're still the blue dot. The red dot is just something moving at random. So it could be, you can think of it as maybe some animal. And when we set this criteria to not modify the state, what the agent tries to do is make sure that the window doesn't break. So it moves it away from the path of the red point so that it's not broken in the end. And if we, alternatively, if we can specify the Wasserstein terminate state, this is a different criteria. So it's the other type of change which I mentioned. And here the goal is to try to make the state as similar as possible to what it would have been if the agent didn't act. So the red dot would have broken the glass, and we want to keep that. We want to let it break the glass and still reach the green dot. And this is what the agent does in this case. And now I give the word to Jobst for some final comments.
Yeah, thank you, Martin. I'm trying to advance the slide. So there's my final slide. There's just a few links that you might want to click on when you find these slides online later on. We just an hour ago, we published the first 3.5 posts in our Lessrom sequence, which will continue, and the whole project will also continue also via SPAR. And we seek collaborators. And if you want to work on some of these things, then please reach out. Thanks.